Back in my day.
Like the beer, there's a craft beer or whatever.
So that's gonna go
25 cups. Yeah, bring it down. It's like, you're so funny. I'm like, dude, you're getting 5 or 6 teams.
Oh, I know like culinary, like, oh, yeah.
It has, like, has a pretty double day, but have you ever
Yeah,
seen
me too. I wanted to go.
I wanted to do it. He's crazy.
All right, this is the last section of chapter 8. And then we're going to start getting into chapter 9, which is titled
Easier stuff.
Applications. Applications of trigonometric functions. So we'll start working with triangles so the plan today, this section is very short. Very short. So I was thinking we would get through the section. I would give you a few problems out of the chapter review that would kind of rehash the last few lectures since the last exam. And then, if we have time, maybe we'll cut out a little early. It's Halloween, and I don't know. Maybe not. We'll just see how things go. Not that I'm going to go anywhere. I'll still be around campus if you want. We can. I'll stay here and do more problems if you want. I'm just saying.
What days are your office hours?
What days? Every day,
Your
except
office
Friday.
hours every day?
Yeah, but they're not at the same time every day. You can get to the syllabus, right, on Canvas. It's listed there.
Okay.
Yeah. No, it's okay. But I can't. If I. Yeah.
I can understand. There's a lot in there.
Okay, so we have two new sets of formulas. I wish I could say that we have 2 new formulas and that's it, but these are actually 2 groups of formulas that are on the formula sheet. And I'll tell you right now, I do not have these memorized. Okay, so I don't have them memorized. I've been doing this for a long time because I understand they're used seldomly used formulas, but when you need them, you need to know that they exist. All right, and that you need to know where to go get them. All right, so let me put the first one up here. Sine alpha times sine beta. So I'm putting a dot between these, even though the formula doesn't have the dot. That's to help you see that this is a product, right? Equals 1/2 bracket. All right, cosine of alpha minus beta, and then minus cosine of alpha plus beta. Now, do you think this is a product to sum formula or a sum to product formula? What is it taking? A product and it's turning it into a sum. It's a difference, but sum and difference. This is subtraction is just another way of adding something, right? You add the opposite. The important thing is that you've taken a product of 2 things and you have split it off into 2 terms, right? 2 terms. And sometimes it's very useful to be able to do something like this. All right? Sometimes meaning down the road, down the math road later. You may need to take a product and split it out into 2 pieces. This allows you to do it. So this is an example of a product to sum. Now there's 2 more. And should I write them down? Do you want me to write them down? I'll write them down. They're in the book, but I'll go fast. Cosine alpha cosine beta equals 1/2. So that seems to be the common theme, 1/2 out front. Cosine alpha minus beta plus cosine alpha plus beta. So very similar to the previous formula, right? What's the only difference? Plus. Okay? And then the last thing we have is sine alpha cosine beta equals 1/2 sine alpha plus beta plus sine alpha minus beta. All right. And those are the only formulas that are listed. This takes care of all possibilities. If you've got two different sines, right, sine of alpha, sine of beta, you can split those up into two terms. If you have two cosines being multiplied together, you can split that into two terms. And if you have a sine and cosine, then you can split that into two terms. Those are the formulas that we would use for those. I'm not going to prove these. Let's just do an example. Sine 6 theta times sine 4 theta. Okay, so convert to a sum. So this, right, as it appears, sine 6 theta times sine 4 theta, there's nothing wrong with that expression. It's not complicated. It's just two things being multiplied, right? So again, why would you need to split it? Because later on, I can think of one example right off the bat in Cal 2, where if we were asked to integrate that, we could not integrate that easily. But if we could split it into two pieces, then we could integrate it easily. So we would want to go to this first formula and split it up into two pieces, all right? So this will be using that first formula. This should be equal to what then? 1/2, right? Cosine. And you have an alpha and a beta, right? So my alpha in this case is 6 theta. My beta is 4 theta. So we should have cosine of 6 theta minus 4 theta minus cosine of 6 theta plus 4 theta, which is 1/2 cosine 2 theta minus cosine 10 theta. And you could leave it like that, or you could even go, like if this was a Calculus 2 class, you would probably want to split this up and distribute the negative or the 1/2 through. So just pass the 1/2 through the brackets.
So we can subtract it?
You cannot subtract these. Yep. No, these are not like terms. In order to subtract or add cosines together, you must have the same arguments inside, and we don't have the same arguments.
Can you factor in the cosine?
No. No. You mean just like the three letters COS? You cannot. Yeah, because cosine, the COS in front is the name of the function. It's not actually like variables in the problem that we can pull out. Am I making sense? Okay. That's it. We're done. We have turned a product into a sum.
We're not going to multiply in the 1/2?
I did. I passed the 1/2
Yeah,
through
you
here.
just left it in there.
Yeah, I cannot put it in here.
Oh, okay, that's what I was
Yeah,
wondering.
yep.
How's that?
When it comes to trig functions, the argument here, you can't touch that argument, all right? You can't pull numbers out of it. You can't multiply numbers into it. I was showing some other students one of the things that I remember seeing as a student is something like this. If you have like sine theta over theta, right? This theta is inside the sine function, right? So this is legal or not legal? Not legal. And what is that if I do this? This is a sin, right? See, that's all that would be left. And that would be a sin. So you're not allowed to do that. No sinners in here. I don't want to create a bunch of sinners here. All right, it's kind of dumb, but if it helps you remember, So arguments are always trapped. Let me give you another example. If you had like sine 2 theta, can I just pull the 2 out?
No.
No. Now, is there a formula for this?
Yeah.
Yeah, from last class, this is actually equal to 2 sine theta cosine theta. That's the formula for, if you want to do anything to that, where it's not a theta inside, you have to use the formula to do it. Algebraically, you cannot just pull a 2 out. Okay, that's it. Let's see if there's another example. Yeah, that's... How about sine, let's do sine 3 theta cosine 5 theta. Sine 3 theta times cosine 5 theta. Same instructions here. Convert to sum. So I'll use the last one there, right? One half bracket. This is going to become sine of alpha plus beta. What's alpha plus beta here? 3 theta plus 5 theta, which is 8 theta. And then plus sine of alpha minus beta, which is 3 theta minus 5 theta, which is negative 2 theta. Are we all on board with that? Okay. That would be it. I'm going to pass the 1/2 through.
Shouldn't that be a positive?
What?
Negative.
What?
Shouldn't it be a
What?
positive half sine negative 2 theta?
What?
I mean, the formula says
Did you
positive,
factor out a
right?
negative or what?
I don't know. What the hell did I do?
You get
Okay,
plus
you
and
factored out a
minus.
negative. Okay.
I'm not allowed to factor anything out like that.
All that stuff says plus.
Sine negative 2.
I have not made a mistake.
Oh, there are
I make
similar
mistakes.
functions, like odd and even?
There we go. Okay, good. This sine function is an odd function, which means that if I replace this angle with a positive angle, it's the same thing except that it's negative. Now, the only reason I chose to do that was because I don't like negative angles inside, and I wanted to illustrate that I could do that. And the book most likely would do that and write that. That would be the answer in the back of the book. You'd be like, what the heck? It's supposed to be this. So from here to here, we are not pulling a negative out. We're using this odd property of sine, that sine of negative theta is negative sine of theta. Good.
Just looks better.
Just looks better. Yeah, I mean this, yeah, it's subjective, right? I mean, what looks better is subjective.
You can just swap the sign, that's it.
Yeah. Now, let's see here. Let's do one more of these just to see. Let's do this. Let's go cosine, cosine. So same thing, but let's go cosine 3 theta and then times cosine 5 theta. So this will become, from the second formula, 1/2 bracket cosine of alpha minus beta, right? So negative 2 theta, and then plus cosine of 8 theta. How could I write that if I wanted to? Just cosine 2 theta, right? I could pass the 1/2 through, but I could just write cosine 2 theta instead of cosine theta. And see, there's no factoring anything out. That's not what's happening here. Using the fact that cosine is what? What type of function is that again?
Even.
It's an even function. The negative is this. If you plug in a negative angle to cosine, it's the same as plugging in the positive angle. So that means we can just replace it completely with 2 theta. Okay. That takes care of the product to sum. Let's look at the sum to product. So sometimes, other times, there's a way to start off with 2 functions being added together or subtracted and then put them together into a product, which can be useful. When have we ever in our lives wanted to look at something and that has a bunch of terms in it and turn it into products? Have we ever done that? Have we ever in our lives had something that looked like, I don't know, like that, and then we wanted to turn that into products, like something times something instead? Yeah. That's called factoring, right? So you could actually, this formula from sum to product is a way that you could factor something if you needed to, because you're going to be able to turn things into multiplication, convert from addition or subtraction to multiplication. Now it's not going to look that pretty, but here it is. So sine alpha plus sine beta equals 2 sine of alpha plus beta over 2, and then cosine of alpha over beta, it's alpha minus beta over 2. So that's the first formula. We have a formula for sine plus sine. We have a formula for sine minus sine. We have a formula for cosine plus cosine and cosine minus cosine. So there's 4 for this one. Sine alpha minus sine beta. You need to memorize all these. By the end of class, we're going to have a quiz over this at the end of class.
If you actually read the
Happy
first
Halloween.
chapter, it tells you that.
Happy Halloween, everybody. And I'm going to count it as an exam grade. So, no. No, remember I said I started this whole thing off today saying I don't have these memorized because I don't believe it's worth your space in your brain for this. So you will have that on the test. You will have the formula sheet that's in the back of the book. You can have that on the next test. And they're right there. They even say, product to sum and sum to product right there. You don't have to remember them. If you do, good for you. Some people can just do that, like they can just memorize stuff like crazy. I'm not like that.
I think I accidentally memorized stuff and sometimes don't remember what I memorized.
Some people can just look at something, that's it. They see it once and it's there. Savants, yeah. Like the guy I was telling you all about that memorized pi out 60,000 digits. Remember that? Did I tell you all? I told you all about that, right?
I don't think so.
No? Oh. The world record for, well, you all know that the number pi is irrational, meaning that it goes on forever, there's no pattern. So people have been trying to memorize it for a long time, right? They've been like, like before calculators especially, it used to be like a measure of how big of a dork you were, like how far you knew pi, There's actually a faculty member that I will not mention that works here who's in their 60s. I think they're getting close to their 70s. And I went to his 60th birthday party at his house. I was invited, and I went there, and his daughter-in-law was a baker and created this cake. It was incredible. It was a cake that looked like a brick, okay? A very long brick like this. And it was about, well, that's probably a little small. It was probably, in real life, it was probably like that, okay? So you could cut this cake. And, but it was probably as long as, like from my book bag right there to about right here. And she had put on there those wax candles that are numbers, right? And it looked like it. And so he had no idea about this cake, right? So they said, time for the cake, and they had put this cake in this room by itself. They walk him in there, and we had been drinking a little whiskey, And he was a little happy at that point, and he walks in the room. He sees the cake, and what she had on this cake was all the wax numbers was pi. It was 3, 1, 4, 1, 5, and it went out 60 digits because it was his 60th birthday, right? So it was 60 digits of pi on this cake. So he walks in, right? We're all behind him. He walks in, he sees it, he turns around, and he starts spieling them out. 3.1415, and he goes through the whole thing. He's not looking at it. He gets to the last number, and he asks his son, whose wife baked the cake, he says, did she round the last digit or not? And he said she rounded it appropriately. So he gave the last digit, and it was all correct. So 60 digits. This is an old man who's been drinking. He used to know it out 120 digits. That was his record. But the world record is 60,000 digits. And it was done by a savant who is, I don't know. The way I can explain it is this person does not look at numbers the way that we look at numbers. It's kind of like, the way I look at it is, if somebody asked me right now to describe my morning, I could describe my morning in great detail. You know, I could talk about when I got out of bed. I could talk about where things are on the nightstand. I could talk about that towel, that white towel that's been there for 3 days is still sitting right there in the corner. Like, you know what I'm saying? Like, I can go into detail about my room. I can walk through. I can, talk about where things are on my counter. Walk into the living room. Okay, I remember there's that marker that was still on the table. Like, he sees numbers like a scenery. And so recalling it is like just kind of walking through this thing in your mind again. And 60,000 digits, and he stopped because he was exhausted. It took 8 hours to recite it. So, and someone's checking the whole time.
Someone stands there from
Somebody's checking the whole time. Now, is that useful? No, probably not.
But it's pretty interesting.
But they study savants. These people have very different perspectives on things because they can do some incredible stuff.
How long did it take for him to memorize all of them?
I don't remember. I did see in an interview, he did talk about how long he had studied it. I want to say it was several weeks. Yeah, several weeks. Yeah, but okay. Yeah, so if you're a savant, there's no problem probably, right? But if not, then you just got to rely on the formula sheet. Wait a minute, cosine alpha, cosine beta. And then equals 2, negative 2, negative 2 sine alpha plus beta over 2, and then sine of alpha minus beta over 2. Just make sure you get that negative sign here. There we go. Do you notice that we do not have a formula for sine minus cosine?
Yep.
Right? There's not one here, right? We can do sine minus sine, sine plus sine, sine minus sine we can do. Cosine, cosine, cosine minus cosine, but there's no sine cosine combination. All right, let's do one here. Let's express sine 3 theta minus sine 6 theta. Convert this to a product. So I'm going to use the second formula, right? So this should be equal to 2 sine 3 theta minus 6 theta over 2, and then cosine of 3 theta plus 6 theta over 2. 3 theta minus 6 theta is negative 3 theta over 2, and then cosine of 9 theta over 2. This type of stuff that we're doing right here is what we call plug and chug. You're just plugging things in. That's all you're doing, right? There's really not a lot of thinking involved here at all. A little bit. Anything that you might suspect that I would want to do with that I haven't done? That negative inside that sine function, I probably don't like that in there. So I'm going to use the property of sine being an odd function, and I'm going to pull that negative out. I'm not pulling it out, but I'm rewriting this. So this can become a plus as long as I put a negative on the outside. So I can put negative 2 sine 3 theta over 2 cosine 9 theta over 2. All right. That's it. Do another example, though. Example. Solve sine of 4 theta plus sine 8 theta equals 0. All right, now we're solving a trig equation, right? I have not identified at all any restrictions on theta, which means that my solutions are going to be the general solutions, which means they're going to involve the ends, right? I'm not saying just give me the solution between 0 and pi, or 2 pi, right? This is all the solutions. So when you look at this, you can't do anything we've done before with this. Like you can't move one of the signs over and try and divide. You can't pull out a 4 from each of these. Can't do that, right? That's no good. But what could you do? The formula, right? So I can use the formula that would turn this sum into a product, because if this is a product, if I have two things that multiply to be 0, I just set each one to 0, right? Okay, so let's use the sum to product formula for this, which means the left side turns into 2 sine of alpha plus beta over 2, which would be 12 theta over 2. And then the formula is cosine of alpha minus beta over 2 equals 0. All right, so I'm using the first formula I gave you. This is sine of alpha plus beta over 2, cosine of alpha minus beta over 2. Alpha is 4 theta, beta is 8 theta. Y'all okay with where I got that from? Any questions? All right, see, now we have multiplication, and that's a good thing, right? Things that multiply to be 0, you just set each one equal to 0. Let me clean it up a little bit before I do that. This is, 6 theta? And then cosine of 2 theta equals 0. So from here to here, 12 theta over 2 is 6 theta, right? And what happened to the 2? I just divided 2 on both sides and got rid of it. Right? I can do that. Divide this by 2, it's gone. 0 divided by 2 is still 0. Do you agree? Okay, what about from here to here? This is negative 2 theta, but because cosine is even, I can use cosine 2 theta, can't I? Okay. Okay, we have two things that multiply to be 0. So I set each one of them equal to 0. So that means I'm going to set sine 6 theta equal to 0. And the other equation I need to work with is cosine of 2 theta equals to 0. Now this, if you've been doing your homework, is something that you should have some experience with now. Here we want to know where the y-coordinate is 0. And that happens here and here, right? So that means I need the argument of that sine function to be equal to, the argument of sine function 6 theta, I need it to be equal to what?
0 and pi.
0 and pi, but I want the general solution. So how can I cover both these dots with the general solution? N pi. N pi will work. So you basically said start at 0 and just keep adding pi's to move around. Okay, good. And solve that for theta. Divide by 6, and you get n pi over 6. That is the general solution right there. That corresponds to that factor being set to 0. So I have an infinite number of answers right now, but this isn't all of them. I now need to come over here and get this. So cosine being 0 means the x-coordinate, right? The x-coordinate is 0. That happens here and here. So that means the argument 2 theta must be equal to, how do you want to do this?
Pi over 2 plus pi.
Pi over 2 plus pi n, or n pi. And then you solve for theta. Theta is, divide both of these by 2. So pi over 4 plus pi n over 2. You could get a common denominator here, right? And put it, but I'm not going to. Because that's a general solution, I'm happy with that. Right, that would be the solution to that equation. If you pick any value of n you want right now, take that and plug it in here, you should get a true statement up here. All right, we're done. Do you want to check? Do you want to check an answer? I do. Let's let n be 0. What would this be? 0? Sine of 4 times 0, that's sine of 0. 8 times 0, that's 0. Sine of 0, so sine of 0 is 0 plus sine of 0 is 0, so that's true. And that should work for any of those that I plug in. We should get 0. All right, interesting. If you have a calculator, I'd like for you to pull the calculator out and put it in radian mode. This is a little off topic, but it's still within the framework of... And I'd like for you to figure out on your calculator what is sine of 1. And then I want to know what cosine of 1 is.
How many digits?
Just have it ready, okay? I'm going to ask you for the answer in a second, but if you have it, go ahead and look at it, see what sine and cosine of 1 are. Now, the reason I'm showing this to you right now is because I want you to know why we call sine an odd function and why we call cosine an even function. And I actually also want you to know what your calculator just did to get that answer. In Calculus 2, we learn about something called power series. All right? And it turns out, in Calculus 2, that sine of x is equal to 1 minus x plus x squared, no, oops, I messed it up already. 1 minus x squared over 2 plus x to the 4th over 4 times 3 times 2 minus x to the 6th over 6 times 5 times 4 times 3 times 2. I'm going to stop here at this next one. X to the 8th over 8 times 7 times 6 times 5 times 4 times 3 times 2. All right, I can even put times 1 at the end of that if I want. Okay, and this actually, there's a pattern here. I don't know if you can see this pattern, but it continues forever. All right? So what I'm going to do on my calculator is I'm going to plug in sine of 1. I'm going to replace all these x's with 1s. So sine of 1 should be 1 minus, what's 1 squared? 1. 2 times 1? 2. So 1/2 there. Plus 1 to the 4th? 1 over 24. And then minus 1 over 720, I believe it is. And then plus, I'm not going to do this one. So on my calculator, I'm just going to figure out what's 1 minus half plus minus 1. Okay, now I want you to go back and look at sine of 1. What did you have for sine of 1? What did you get? 0.54, right? I got 0.540277. What did you get? 0.54 what? 0.3. I got 0.54027. We're off. We're off. The reason we're off is because I stopped. If I keep going, I'm going to get closer to that answer. All right? If I could go forever, I would actually get the exact answer. When you type sine of 1 into your calculator has no idea what the sine function is. It's actually evaluating this, this is called an infinite series. It's evaluating this infinite series. Because your calculator can do several things very well. It can add and subtract very quickly. It can multiply and divide very quickly, right? So when you type sine of 1 in, it can do this thing right here, right? Like I was squaring and multiplying. Like the computer can do that. It could go out 1,000 of these and do that like that, right? So that's what's happening. That's what's actually the brains inside your calculator have been programmed to say that this is what sine is. All right, now I'm going to show you what cosine is. Cosine of x is equal to x minus x cubed over 3 times 2 times 1 plus x to the 5th over 5 times 4 times 3 times 2 times 1 minus x to the 7th over 7 times 6 times 5 times 4 times 3 times 2 times 1. And plus dot, 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 and this keeps going. Does anybody see anything that relates to why I was saying even and odd functions? Yeah, exactly. Look at the powers. Look at the powers on all of these x's for sine. Yeah. For
sine, yes.
For sine, yes. Wait a minute. Hold on.
Sine's even, right? Cosine's
No.
Cosine's even.
No. Hold on. When I asked you what was sine of 1, what did you tell me? 0.54?
0.841.
Sine, okay. Was that cosine?
Yeah.
Okay, I've got these backwards. Sorry. I've got these backwards. This is sine. This is cosine. Sorry, I've got them backwards. I have no idea why I did that.
Halloween,
Yeah. So we said cosine was an even function, right? Cosine is this. And all the powers on the x's are even. All right? Sine, all the powers are odd. And that's not a coincidence. That's where it all comes from, the idea of even and odd. So when you're taught in college algebra a function is even or odd, it's very difficult back there to understand why they're calling it even or odd. But it's because every function out there pretty much every function out there, can be rewritten in what we call its power series expansion. And its power series is either going to have evens or odds or mixtures of even and odds. If it's a mixture of even and odds, it's not odd or even. Because remember, functions can be odd, even, or neither. So if you got them all mixed up together, you wind up getting something that's not even or odd.
I think you had it right the first time, because on mine, sine is even and cosine is odd on my calculator. This one. So,
What do you mean even?
as in, like, cosine is 0.5403 and my sine is 8.841.
Yeah, that's what I'm saying. Cosine of 1 should be 0.54.
Okay.
Yes. I said sine of 1 was 0.54, but I used that formula to get it, so yeah.
Yes.
It's right. Cosine is even. You seen that function before? Yes? Here's its power series expansion.
That forever.
Yep, the same pattern forever. Okay, so do you see a difference between this one, and this one? This one is not switching positive and negative, right? It's not. And this one has both evens and odds in it, right? Powers. But this is, when you type in like e squared on your calculator, right? If you type in e squared, it's plugging in 2 right here, 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 and it's calculating it and it's giving you a decimal. How many of you, again, need to have Cal 2? How many? And how many don't? Yeah, so that's why I'm getting, I'm trying to lead half of you into something that's more interesting later, but yeah, all right. I told you that was going to be a little off, but please understand that your calculator is not smarter than you. I mean, all it knows how to do is addition, subtraction, multiplication, division. That's all it can do. That's it. So when you type in sine, it's not sitting there going hypotenuse, adjacent, opposite. It's not doing that, right? It's just applying a formula. Yeah, it is pretty smart, It might be smarter than you. I take that back. It might be smart.
This thing's pretty expensive.
All right. Let's do a couple of more things here, man. You're not going to like this. Show that that cosine theta minus cosine 5 theta over sine theta plus sine 5 theta. Make sure I'm getting this right here. Equals tangent of 2 theta. This is an identity. We need to prove it's true. So we start with one side, turn it into the other, right? The better side to work with would be the left side, because it's got more stuff to work with. So, any ideas? Can we just turn this into cotangent and this into cotangent? No, because they're split up by addition and subtraction, so can't do that.
Can we separate them to have common denominators?
Separate them out into 2 different fractions? You could do that. You could.
But you use formulas.
Yeah,
You should formulas.
Formulas to plug in the top.
You mean the formulas from this section?
Yes. I think so, maybe.
I think maybe.
Possibly.
Possibly.
Putting it out there.
I think there is a way to turn this into 2 things being multiplied, right?
Yeah, cosine
And then there's a way to turn this into two things being multiplied. Then you can cancel things out. If things cancel, you will be able to cancel them, right? The reason you can't cancel them now is because you have subtraction and addition here. So let's apply the formulas for that. Now you'll have to reference something, or you'll have to believe me if I write it down. I'm not going to rewrite the formulas though, right? This top one is cosine alpha minus cosine beta. So that turns into, just the top there, is negative 2 sine of alpha plus beta, which would be 6 theta over 2. And then sine of alpha minus beta. What's alpha minus beta? Negative 4 theta over 2. That's what the top is. That's negative 2 sine of alpha plus beta over 2 times sine of alpha minus beta over 2. Over, by the way, this was the left-hand side. Over, now sine plus sine becomes 2. Sine of alpha plus beta over 2. And then times cosine of alpha minus beta, which is negative 4 theta over 2, like that. And a lot of things just got really nice, didn't they? I'll write some more here. Negative 2 sine of 3 theta, sine of negative 2 theta over 2 sine 3 theta cosine of negative 2 theta. So what can I do at this point?
You can cancel off 2 sine theta.
Okay, I can cancel off the sine 3 thetas. Those can go away now. But the 2's, right? This 2 and this 2, I'm still left with the negative 1 upstairs, right?
Positive when you take out that negative from the sign.
Yeah, look at our answer. Our answer that we want to get to is sine of 2 theta, not negative 2 theta, which means we need to convert both of those negatives over to positive thetas, right? So let's use our property here. First, we have a negative 1 out front, right? I'm just going to put it like that. That's my negative 1 out front. Sine of negative 2 theta can be rewritten how? Negative sine of 2 theta. And then how can I rewrite cosine of negative 2 theta? Cosine 2 theta. And then this negative and negative go away, right? And that becomes a plus. So I have sine 2 theta over cosine 2 theta. They have the same argument. Sine over cosine is tangent. See how that works? Yes.
Do something that involves like cosecant and like cotangent?
Yes, I'll do something. Let's do something with cotangent in it. I'm going to look for one here. All right. Oh, show. Yeah, we want to do this again. Show that cosine alpha plus cosine beta over cosine alpha minus cosine beta equals negative cotangent of alpha plus beta over 2 times cotangent of alpha minus beta over 2. Does that one look appropriately ugly to you? Yeah. All right, same story. You want to start with the left-hand side here? Yeah? Start with this side. Let's use our formulas that'll convert a sum into a product, sum into a product. So I'm going to have for the top one, it'll be 2 cosine of alpha plus beta over 2, then cosine of alpha minus beta over 2. And then the bottom one becomes the negative 2 cosine, oh no, sine, sorry. Sine of alpha plus beta over 2, and then sine of alpha minus beta over 2. Those are just directly from the formulas. I think this one's going to be somewhat straightforward at this point. Almost. I know you want an example of one that's going to be more difficult because it has cotangents and stuff in it, right? But this.
In the homework, it was really hard. Like when there's a cosecant, like in the previous section,
Mhm.
I didn't get it.
Okay.
Yeah. So
Okay.
I thought maybe it's-
Yeah, this one I think is going to be, because look what happens here. Like what's this right here? What's cosine of alpha plus beta over sine of alpha? What's cosine of alpha plus beta over 2 over sine of alpha plus beta over 2? That's cotangent of alpha plus beta over 2. So that's this. What's this? Well, that's that, right? And then 2 divided by negative 2 is negative 1. So, I mean, it's there here. I'm looking at the problems from the section here, and I don't think they get any worse. Yeah. I did see something that really, when I saw the problem, I really was like, whoa, that looks good. That looks fun. It was this one. This is out of the chapter review. It's the instructions here are to find the exact value. And what they mean by that is you can't use your calculator here to like try and figure out what the answer is. So here we go. What is cosine of arc sine of 3/5 minus cosine inverse or arc cosine of 1/2? And I'm going to put the arguments of those trig functions in parentheses. I don't remember seeing a problem like this in any of the sections, but it's in the chapter review.
So it's like a formula cosine alpha minus beta.
It's like a formula what?
Cosine alpha minus beta.
Oh, so you're saying like treat this whole thing right here like alpha and this whole thing like beta? And then you could apply that formula, cosine of alpha minus beta. Could we do that? Sure, we could. When you have an inverse trig function, right? It's going to spit back an angle, isn't it? So that could be an angle, alpha. This is going to inverse trig function. It's going to spit back an angle. So I could call that angle beta.
I'm sorry. What if you can do like like we know the value of cosine of negative 1/2 on the unit circle,
Yes.
and 3/5, you could do that as a reference triangle and
Yes.
get a value, and then kind of solve for the cosine. Is that possible?
Well, we would get a reference, but it would not be a common one, right? So we would not be able to get the angle, the precise angle, could we?
No.
No. If these were both common values, then we could probably do this without doing the formula at all. But because this is 3/5, we're not going to be able to recover alpha exactly. without a calculator. So let's keep going, okay? Let's keep going. I like the idea of using a formula for cosine of alpha minus beta. The formula for cosine of alpha minus beta, we just did that, didn't we? Is -2 sine, I'll write it up here, -2 sine of alpha plus beta over 2 sine of alpha minus beta over 2. That's the formula for cosine of alpha minus beta. All right, that's our formula. So applying that to this, it would become -2 sine of, all right. Uh-oh.
Sir, can we do the cosine alpha cosine beta plus sine alpha sine beta, like that formula?
Which one?
Cosine alpha cosine beta plus sine alpha sine beta.
Cosine alpha cosine beta plus sine alpha sine beta? What about that one? You want to use that one? That's what? Cosine of alpha minus beta, right? That's this one right here?
Yeah, can we do that one?
For you mean at this step right now?
In this problem? I don't know.
Okay, well, I'm not disagreeing with you yet. Let's see what we have first. Let's see what we have. Right now, according to this formula, this is going to become -2 sine, right? And then alpha plus beta over 2. Alpha is this, right?
3/5.
Plus beta, which is this. All over 2. Let's just appreciate how ugly this is about to look. Sine inverse of 3/5, that's alpha, plus cosine inverse of 1/2, all of that over 2. Do y'all agree that that is just sine of alpha plus beta over 2? Yes? What do I still have? Sine of alpha minus beta? Over 2? What do y'all think? What was your name again? Sophia.
I'm kind of confused because that's what we're gonna use that formula. You know, like I kind of don't get why we're using.
Oh, okay. All right. So so the formula I used here is not the one you were suggesting I use?
Yeah, I was suggesting that word, but I get it.
Ah, okay. So what is this what I wrote up here correct or incorrect?
Correct.
Is this correct or incorrect?
Shouldn't it be subtraction right there on the second sequence?
Did I miss? Oh, I did miss. Okay, yeah, I did miss that. But this I did miss. Okay, is it correct?
Yes. Okay, well, I don't know about this, the R side. It's not cosine.
I realize that today is the first day you're seeing these formulas. So I'm doing something here intentionally to see if you're going to catch me doing something that I'm sure someone in here is going to do. This is not right at all. But why is it not right?
Because this is not cosine minus cosine. Like,
This is not, okay, so I said here, hey, we could look at this as cosine alpha minus cosine beta, right? And then I said, we just had a formula for that. And the formula we have, I wrote it up here, was what? What's this formula for? What is the formula I just used here for?
Sum product.
It's cosine alpha minus
cosine beta.
cosine beta. Isn't that what we have here?
No.
No. Right? Okay. Do you see the difference? This right here, cosine alpha minus cosine beta, is not the same as cosine of alpha minus beta. right? These are two different expressions.